learned how to name. And so in chapter 3, we've introduced Lewis structures, and we're focusing on molecular compounds when we're drawing Lewis structures. And so Lewis structures are structures for molecular compounds. Now in chapter 4, which I think most of us in our lecture classes will be starting that next week, we're going to focus on ionic compounds in chapter 4. Ionic compounds have ionic bonds. Ionic compounds consist of a metal and a nonmetal. And what happens to form an ionic compound is that the metal atom will donate one or more electrons to the nonmetal, and the ionic bond is formed as a result. But in chapters 2 and also with Lewis structures in chapter 3, we're focused on molecular compounds. And with molecular compounds, there is no transfer of electrons, but there is a sharing of electrons between non-metal atoms. And this sharing of electrons creates a covalent bond. So molecular compounds have covalent bonds. Covalent bonds are also sometimes called molecular bonds. And therefore, molecular compounds are also called covalent compounds or covalent molecules. So molecular molecules are covalent molecules. They contain only nonmetals. And so when two nonmetal atoms come together to share electrons, the question is, well, which electrons will they share? They're only going to share their outermost electrons. And so if we take a look at an oxygen atom, oxygen is atomic number 6. Atomic number 6. So it has 6 protons. In its nucleus. I think the most abundant isotope of oxygen has 8 neutrons also in the nucleus. And so we learned also, when we learned atomic structure in chapters, I think it was chapter 2, that in the nucleus are your neutrons and your protons. Surrounding the nucleus are the electrons. And the electrons reside in these orbitals. So these little circles that I'm drawing around the nucleus, those are orbitals. Each of these orbitals has a different energy. So we talked a lot about wavelength and frequency in chapter 3. And we also talked about how electrons act like packets of energy called photons. And we also said that light or electromagnetic radiation in general also behaves like a packet of energy called photons. And so with the electrons residing in these various orbitals, each of these orbitals has a different energy. And they have different energy because each of these orbitals are a certain distance away from the nucleus. The farther the orbital is away from the nucleus, the higher the energy. And so an electron that resides in the outermost orbital, so there's one of the electrons of oxygen. So if it has 6 protons, it also has 6 electrons. 2 let's see. It is actually atomic number 8. I have to remember. Let me make sure. You take a look at a picture of a periodic table to make sure I'm correct. Yes, it is atomic number 8. So 8 protons and 8 electrons. Oxygen is also a member of group 6. So it has what we call 6 valence electrons. And so therefore, what that means is that 6 of the 8 electrons of oxygen are going to be in this outermost orbital. The other 2 electrons are going to be in this orbital that's closest to the nucleus. And so this is energy level 1, energy level 2. And that lowercase n, if you go on to take general chemistry, you'll learn more about this. It's called the principal quantum number. And that gives you the energy level orbital number. So the outermost energy orbital of oxygen is going to contain the outermost electrons that we call valence electrons. And because oxygen is in group 6, that tells us how many valence electrons that atom has. It's based on the group number. So oxygen has 6 valence electrons, and therefore it has 2 what we call inner electrons that lie in the orbital closest to the nucleus. So these 6 valence electrons are going to have a higher amount of energy than the 2 inner electrons that are closest to the nucleus, because those inner electrons are going to feel the force of that positively charged nucleus more than those electrons residing in the outermost energy level. So therefore, when we talk about forming a covalent bond and therefore sharing electrons, those valence electrons residing in that outermost energy orbital, those are going to be the ones involved in bonding. Those are going to be the electrons that are going to be able to be shared with another atom and therefore create a covalent bond and therefore create your covalent molecule. And again, the number of valence electrons is the same as the group number. So we said that oxygen, we use that as our example, residing in group 6, has 6 valence electrons. So therefore, an atom of fluorine resides in group 7. So a fluorine has 7 valence electrons. The noble gases make up group 8A. So therefore, they have 8 valence electrons, and they are stable. So because of having these 8 electrons in their outermost energy level orbital, and that being the most stable arrangement is having 8 valence electrons, the other nonmetal atoms like oxygen or nitrogen or carbon or sulfur, they therefore have one goal, and that is to strive to have 8 valence electrons Testing, can you hear me? Use the hand wave to confirm. Can you hear me? Thank you. Sometimes it works just to leave the room and return, and I guess that solved the issue. I'm not sure when you stopped being able to hear me, but I used the oxygen atom as an example of explaining what valence electrons are. And I also went through talking about the Octet Rule. When two nonmetal atoms come together to form a covalent bond, they share electrons. And in sharing electrons, their goal is to be like the noble gases. The noble gases in group 8A, they have 8 valence electrons. So the other nonmetal atoms, their goal in making a covalent bond with another nonmetal atom through the sharing of electrons process, their goal is to obtain 8 valence electrons. So like oxygen, it only has 6. When it makes a covalent bond, let's say with a carbon atom and forming carbon monoxide, oxygen's goal is to go from having 6 valence electrons to 8 valence electrons. And where is it going to get the other 2 electrons from? From the carbon atom. Goal, starting out, is in group 4, so it only has 4 valence electrons. When it makes the bond with the oxygen atom, its goal is to go from having 4 valence electrons to having 8. And that's what the octet rule is. When forming covalent bonds, those nonmetal atoms that are not group 8A atoms, their goal is to obtain 8 valence electrons through the sharing and covalent bonding process. And so we've looked at drawing Lewis structures in our lecture. We've seen probably many different examples. I know in my lecture, we've drawn several Lewis structures, some of which you'll see today that you'll get practice drawing again. And so one of the more simple Lewis structures to draw is methane. Methane's formula is CH4. So in going through the rules for drawing Lewis structure, we're going to apply those rules and we're going to draw the structure for the methane molecule. And so once you know the formula of the compound or molecule that you're required to draw the Lewis structure of, you've got to figure out which atom in that formula is the central atom. Usually the central atom in a molecule is listed first in the formula. So by this convention, carbon, of course, then would be the central atom for methane's Lewis structure. All the other atoms, in the case of methane, the 4 hydrogens, are going to then be attached to the central carbon atom. But there are some exceptions to this. If hydrogen is ever listed as the first atom in the formula of a molecule, then hydrogen can never be the central atom. And the reason why is because hydrogen is an exception to the octet rule. Hydrogen is happy with only having 2 valence electrons around it in a Lewis structure. So therefore, hydrogen can never be the central atom. So once you've picked out the central atom, and there are 2 other ways to determine the central atom. So we talked about the first method. The first atom in the formula is usually the central atom. And then we also said that hydrogen is never the central atom because it's an exception to the octet rule. But there's a third method or rule in determining the central atom. The least electronegative atom in the formula for the molecule or compound is going to be the central atom. Well, how do you know which atom is the least electronegative? You would need to know the periodic table trend for electronegativity, which is shown here. And so electronegativity increases as you move from left to right across the periodic table. Electronegativity also increases as you go from the bottom of the periodic table to the top. So if I have this compound, Cl3F, which atom is going to be the central atom? Will it be one of the chlorines or will it be fluorine? Well, in group 7A is where both fluorine and chlorine reside. Which is the least electronegative, chlorine or fluorine?
Chlorine.
Right. So in the molecule Cl3F, one of the chlorines would be the central atom in your Lewis structure. The other two chlorines and the fluorine will then be attached to the central chlorine. Like so. What about SO2? Both sulfur and oxygen are in group 6. So which is least electronegative, sulfur or oxygen?
Sulfur.
Very good. What about our cyanide ion, Cn? Carbon is in group 4. Nitrogen is in group 5. Which is least electronegative, carbon or nitrogen?
Carbon.
Very good. So if we have the molecule HCN, we know that hydrogen can never be the central atom. And so we've got to choose between carbon and nitrogen. So between carbon and nitrogen, carbon is the least electronegative. And so therefore carbon will be the central atom for the HCN molecule. So that's how you use electronegativity trend to therefore decide what atom in a formula is the central atom. It's always going to be the least electronegative atom in the formula of that molecule. That's going to be your central atom. So those are the 3 things you want to consider when trying to pick out which atom is the central atom. The general rule that usually, but not always, usually the first atom in the formula is the central. Using electronegativity trends gives you a second way to make sure that you're picking the right central atom by choosing the least electronegative atom in the formula. And then just remember, hydrogen can never be the central atom. So for our CH4 methane example, carbon will be our central atom. And then step 2 we need to count the total number of valence electrons that methane CH4 has. You add up the total number of valence electrons by adding up the valence electrons, individual atoms that make up the molecule. So for CH4, it contains carbon. You take the number of carbons in the formula, there's only one, and multiply it times the number of valence electrons for a carbon atom. Carbon is in group 4, so it's going to have 4 valence electrons. Hydrogen is in group 1, so it has 1 valence electron, and there's 4 of them in the formula, so 4 times 1, that gives us 4. Add those numbers together and gives you the total valence electrons for methane is 8. So now we can draw our skeleton structure for our Lewis structure. Our carbon is our central atom. So we're going to attach the 4 hydrogens to the central carbon via a single line, which indicates a single bond. And that's our covalent bond. So now we count how many electrons we've put into our Lewis structure. Each of these single bonds represents 2 electrons. So therefore, that's 2 electrons, 2, 4, 6, 8. So we've added the 8 required valence electrons. But once we get to this step, and if we haven't added all required valence electrons, then we would need to add the additional electrons by putting those additional electrons in pairs. You'll always add them in pairs. And those lone pairs, and you'll put those lone pairs of electrons around the outside atoms. The outside atoms are the ones that are connected to the central atom. In some textbooks, they're also referred to as peripheral atoms. They're on the outside. And so always put those lone pairs and sets around the peripheral atoms in a way that you'll give them a total of 8 electrons around them. Remembering that hydrogen is an exception to an octet rule. Hydrogen is happy with only having 2. Each of these single bonds is 2 electrons. So that hydrogen has electrons around it. This hydrogen has 2 electrons around it. And so do the other 2. And the central carbon has 8 electrons around it. So therefore, the octet rule has been satisfied for that central carbon. And so once you've added the remaining electrons around the peripheral or outside atoms in pairs of 2, giving them a total of 8 around them, if you still have electrons left over, you'll put those lone pairs of electrons around the central atom. And so if your octet rule is satisfied for each atom at this point, and you've reached your total valence electron requirement, then your Lewis structure is finished. But if you run out of electrons before all the atoms are happy and have 8 electrons around them, then you've got to try multiple bonds. And I know for my students, we've talked about double and triple bonds in class. And so therefore, if you added electrons as indicated in the previous step, step 3, it's going to be the central atom then that doesn't have an octet of electrons around it yet if you run out of electrons. So therefore, as I told my students in class, you got to make sure that each of the atoms, except hydrogen, of course, is the exception, make sure that they're happy. And meaning that if they're happy, they have 8 electrons around them. And so if the central atom is not happy, if it doesn't have 8 electrons around it, then you've got to move a lone pair of electrons from an outside atom and move that pair into a bond with the central atom, making a double bond. And if that satisfies the central atom, makes it happy, giving it 8 electrons, then you stop, you're finished. But if the double bond isn't enough to make an octet, then you've got to go to a triple bond. And you got to again take a lone pair of electrons from an outside atom and move it into a bond between that outside atom and the central atom, creating then a triple bond. And so those are the 4 steps and rules for drawing Lewis structures. And so, like I stated, methane is one of those simple ones. There are no double bonds required, no triple bonds required. You got all single bonds in the structure. The carbon is happy. The hydrogens, being an exception to the octet rule, are happy with just having 2 electrons around them. And so the key to getting comfortable with drawing Lewis structures, practice, practice, practice. And that's what we're going to do today. And so when we get into week 9, as I stated, we're going to be able to take the Lewis structures that we're now comfortable drawing, and then we're going to focus in on the central atom to learn about how many bonding groups versus non-bonding groups are there. And then we're going to use that information to determine the shape or geometry of that molecule, and also the polarity of that molecule. And all of that is going to be following what we call the Vsepr theory, which stands for valence shell electron pair is the old term, but in newer chemistry books, the word pair has been dropped and they say group, the valence shell electron group repulsion theory. Most people still call it Vsepr. I know I do. And so this theory is a best attempt to explain why molecules form covalent bonds the way they do. So one premise of the Vsepr theory is that the atoms in a molecule around the central atom, they want to be as far apart from each other as possible. And so that's going to be what determines the shape or molecular geometry of the molecule. And we'll focus more on that in week 9. And so today, what you're going to see for the Lewis structures that we're going to draw, you're going to be seeing pictures of models of those molecules. And based on the models, we're going to be able to therefore determine how many bonding groups of electrons are around the central atom and how many non-bonding groups are around the central atom. So our first model, well, we've already drawn the Lewis structure for methane. So let's just redraw what we've already drawn. Okay. And we already said that carbon is the central atom. So now we're going to focus in on the central atom. Count up the following groups around the central atom. Indicate how many of each there are. Do we have any lone pair of electrons around the central atom?
No.
No, we do not. How many single bonds are around that central atom?
Four.
Very good. How many double bonds are around the central atom?
There are no triple bonds.
Very good. So now let's talk about electron group types. So when you're asked about how many electron groups are around a central atom, there are different types of electron groups. But one thing I want you to really, really understand, each of these different types counts as only one group.
Are we supposed to be viewing your screen? Because I can see you.
You can't see my screen?
No, I can't. I don't know if it's just me or if it's...
I'm logged in on both my iPad and my laptop. And I can see what's on my iPad on my laptop.
I can see the screen. My math professor has this problem sometimes. He just unshares the screen and shares it again, and that fixes it.
Okay, that usually fixes it. Is
Yeah.
everyone having that problem?
I'm fine. So
Okay.
it's usually just for like some students.
Okay, so I just need to unshare and reshare.
I think so.
Okay, hold on one second.
I can see your screen now.
But now my notability is frozen. I can't get back to, there it goes. Now can you see my electron group types?
Yes, ma'am.
Okay, great, that solved it. Okay, so I want you to really understand that each of these electron group types count as only one electron group. So these are our different electron group types. A single bond, a double bond, a triple bond, and then finally, a lone pair. Each of these count as one electron group. Any questions about that?
So that means it can't be a single bond and a double bond. It can only be one, or like...
Yes, it can only be one or the other type. That is correct.
So does that mean since for methane it's all single bonds, does that mean how many total groups are there around for the answer question 4, how many total groups are paired around the central atom? Does that mean that the answer is 1?
No, the answer is 4. Each single bond counts as one group.
Oh, okay, I got
So
you.
if there are 4 single bonds, there are 4 electrons.
Okay. Okay.
So if I have a lone pair of electrons on my central atom, even though a lone pair of electrons is 2 electrons, that's still just one group. Even though a double bond is basically 2 single bonds combined together, that double bond is just one group. A triple bond is essentially 3 single bonds combined together. But that triple bond will still only count as one electron group. Does that make sense now?
Yes, ma'am.
Okay. So now that we've discussed electron groups, now let's answer questions 4 and 5. And I think you already did. How many total groups are around the central atom? 4. And how many of these are lone pair? 0. So these 3 types of groups, the single bonds, double bonds, triple bonds, these are called bonding electron groups. Lone pairs of electrons, those are called non-bonding. Lone pair of electrons is a non-bonding electron group. And that is going to be really important during week 9 when we're deciding on shapes, is knowing how many are around a central atom and how many non-bonding groups. Those 2 pieces of information is what's going to determine the molecular shape of a molecule. So we're going to do one more of these models together. But before we move on to ammonia, if you go to the eLearn page for our lab, and then go to course content, week 7, you'll see that I've placed a document that has models for all of the Lewis structures that we're drawing today. And so there's the model for our methane. And I've got both a traditional chemistry model, what we call a ball and stick model. And next to it, I've got a marshmallow and toothpick model. And they both give us the same information. In the ball and stick model, the black sphere, that's our carbon atom, our central atom. And then in the 4 white balls, and that marshmallow is hiding the 4th ball there in our ball and stick model. But each of those 4 white balls are your hydrogen atoms. And then the sticks between them, those all represent your single covalent bonds. And the marshmallow is telling us the same thing. The pink marshmallow is our carbon. Each of the white marshmallows represent hydrogen. And then the toothpick represents your single covalent bond. Any questions about methane? So model 2A is complete. Model 1A was just the Lewis structure drawing. Model 1 was just the Lewis structure drawing instructions that we went over in detail. So now we're ready to move on to model 3. And so in viewing our model, for methane, just draw a replica of the model that you see here in the picture. You can either draw it as the ball and stick model or toothpick model, it doesn't matter. They represent the same. So here's our central carbon. And here's our 4 covalent bonds. And then our hydrogen atoms. So you just simply draw a replica of the model that you view in the pictures. So now to answer question 7, we know that we've got 4 total groups around the central atom, which is carbon. And these are all bonding groups. We don't have any lone pairs. So what we now do to answer question 7 about the angle. So what is this angle? It's called the bond angle. Do that in a different color. So we need to know that bond angle between the bonds, which we represented as toothpicks in the marshmallow model, or those little sticks in the ball and stick model. Well, to find the bond angle, we go all the way to the end of our document for this week, and the bond angles are listed for us. So how do we use this table? Well, we want to know how many electron groups are in the Lewis structure. And we've answered that question already. I'm having trouble. My document, my notability document is frozen again. Come on. It's not letting me move the screen. Yeah, it's not letting me move. Oh, goodness. Technology. It will not save us. It will let you down sometimes. I may have to log out and come back in again. Give me 1 second. Or I'm going to have to stop sharing and reshare. Oh, it's still frozen. It's not letting me move. There it goes. So now, how do we use this table to determine the bond angle? We go back and find out how many bonding groups and how many lone pairs are in our structure. We've got 4 total groups. None of them are lone pairs. So with 4 total groups, all of them are bonding groups. So we go back to the table. We're in this situation with methane. We've got 4 total groups and none of them are lone pairs. So therefore our bond angle is 109.5. Now, during week 9, it's when you'll be asked this question about methane. What is its electron geometry? Tetrahedron. What is its shape? The shape is also called the molecular geometry, and it's also tetrahedron. But today we're interested in just the bond angle, and it's 109.5. And we put the little degree sign, 109.5 degrees. And the shape that we just saw in the table, tetrahedron. And some books call it tetrahedral. Either term is correct. So now we've totally completed Model 2, both parts A and B concerning methane. So I want to do one more of these with you. And then the remaining 3, I'm going to send you to your group rooms, and you're going to complete Models 4, 5, and 6 within your groups. So our next compound is ammonia. Ammonia has the formula NH3. And so we remember our central atom rules that hydrogen can never be the central atom. And usually the first atom in the formula is the central atom. So we can go ahead and conclude that nitrogen is our central atom. And we can use our single bonds to connect the 3 hydrogens to our central nitrogen. The next step in drawing our Lewis structure is we got to do our valence electron count. We've got a nitrogen. There's only one of them, and that nitrogen is in group 5. So it has 5 valence electrons. Therefore, 1 times 5 is 5. Hydrogen is in group 1, so it has 1 valence electron. And there are 3 of them in the structure. 3 times 1 is 3, giving us a total valence electron count of 8. So is my Lewis structure complete and finished the way it is? How many valence electrons are in my structure right now? 6. Thank you, Sarah. 2, 4, 6. So is my Lewis structure correct the way it is?
No.
Right, because I need 8 valence electrons. I only have put in 6. So how many do I have left to put in?
2.
So where do I put those 2?
They would be a lone pairs at the top of nitrogen.
You are absolutely correct. So now is the nitrogen happy?
Yes.
Yes, it is. Why is it happy?
It has all the 8 electrons required that it needs.
Very good. Nitrogen now has 8 valence electrons around it. The lone pair is 2. Each single bond is 2. So 2, 4, 6, 8. So we've got our Lewis structure complete for ammonia. And so now we can answer the questions. Question 10, nitrogen is the central atom. How many lone pairs are around that nitrogen?
1.
Very good. How many single bonds?
3.
And then there are no doubles and triples. Everyone agree? So now question 12. How many total groups are around our central nitrogen atom? Remember our rules.
4. 4.
4, very good. We got 4 total groups. 3 of the groups are single bonds. The other group is a lone pair. And that's what gives us a total of 4. And of these 4 groups, one of them, therefore, is a lone pair. Everyone agree with questions 9 through 13? So now let's look at a model for our ammonia. And so for the ball and stick model, the black sphere is our nitrogen. The 3 white spheres are hydrogen atoms. And now you notice this stick here that doesn't have a ball attached to it. That represents our lone pair. Our marshmallow and toothpick model gives us the same thing. The pink marshmallow is our nitrogen atom. Each of the 3 white marshmallows are hydrogen atoms. And then the toothpick that doesn't have a marshmallow attached to it represents a lone pair of electrons. And again, you can view these models on your own device by going to our lab eLearn page, course content, week 7, and click on the document for Lewis structure models. So there's our ammonia model. So now based on our model, we're going to redraw it on our paper. We draw our central nitrogen atom. And my 3 sticks that are going to be attached, that are going to be used to attach my hydrogen atoms. And then I'm going to have another stick that I can have there to represent my lone pairs, my lone pair of electrons. And so now that we've redrawn our shape based on the models that we viewed, we again have to answer the question, what's the bond angle? And so again, let's go to the end of this document. We stated that we have 4 total groups. Three of them are bonding groups, represented as single bonds. The other group is a lone pair. Okay, so we got 4 total groups, but this time one of them is a lone pair. So the bond angle is going to be a little bit smaller in ammonia than in methane. The bond angle in methane is 109.5 degrees. But for ammonia, it's going to be 109 degrees. Because of that lone pair of electrons sitting on that nitrogen central atom, it kind of makes the bond angles shrink slightly. And notice also that the shape for ammonia is not going to be tetrahedron. It's going to be trigonal pyramid. Any questions about Model 3? So now you have 3 more models to complete. Model 4, you're going to be doing the Lewis structure for water. And do parts A and B, just like we've been doing. Model 5, ozone. We've been talking a lot about ozone in lecture this week. And then finally, Model 6, carbon dioxide. And so now I want you to go into your individual group rooms and complete models 4, 5, and 6. And then once you've completed models 4, 5, and 6 with your team, return to the general meeting room. And that way you'll have an opportunity to ask any questions that you have about models 4, 5, and 6. And then we'll talk about your final task for today. So we completed models 2 and 3 together in about 30 minutes. So I would assume it's going to take you about maybe 40 to about 40 minutes or so to complete models 4, 5, and 6. So let's return to the general room between 12:50 and 1 o'clock. So as soon as you're finished, just return to the general room. I'll be keeping an eye on the general room, making sure most of us have returned. And during this time period, I'll also be popping in to your meeting rooms to see if you have any questions for me. So now please go into your individual group meeting rooms to finish the remainder of the models for today. Make sure that when you get on part B for models 4, 5, and 6, that you have the pictures of the models from our eLearn Lab page downloaded so that you can view those pictures while you're completing part B for each of the models. I'll also show those models on the screen in the general room. Again, please go to your group meeting rooms to complete models 4, 5, and 6. In the chat box, I'm going to post the group assignments. I do believe most of us are back in the general room. So now I'm going to open the floor up to you for you to ask me any questions that you have on models 4, 5, and 6.
I was kind of stumped on 33.
Okay. So number 33 is for model 5, which is ozone. And so you drew your Lewis structure for ozone. Probably looked like this. And so there's an oxygen atom, that's the central atom. Around that central oxygen, there's one lone pair, one single bond, one double bond, no triple bonds. Everyone agree with that? So how many total groups are around the central atom?
Three.
Right? And of those 3, 1 are lone pairs, correct? So therefore, for ozone, going to the document at the end, we've got 3 total groups, one of which is a lone pair, so the shape is bent. The bond angle is 120. On the other hand, for water, your Lewis structure of water should look like this. We got an oxygen central atom. We got 2 lone pairs on that central oxygen atom, 2 single bonds, no doubles and no triples. So how many total groups around that central oxygen atom? Answer to number 20? Anyone?
4.
4? How many of these 4 are lone pairs?
2 of them.
Very good. So now let's go back to our data table. So we said that ozone fits this description here, in that row of the table. Water, on the other hand, we said there were 4 total groups around water, and of those 4, 2 were lone pairs. So water's description would be at this row. Both of their shapes are the same, bent, but look at the difference in the bond angles. So even though they have the same shape, they have different bond angles because water has a total of 4 groups, 2 of which are lone pair, but ozone only has 3 total groups around its central atom. Both of them have a central oxygen atom. Water's central atom is oxygen. Ozone's central atom is an oxygen. But the difference is that the central oxygen atom of water has a total of 4 electron groups around it, 2 of which are lone pair. But the ozone central oxygen atom only has 3 groups around it, and only 1 of them are lone pairs. And that is what attributes to the difference in the bond angles. Even though they both have a bent shape, ozone's bond angle is larger than water's, because water has those 2 lone pairs on the central oxygen. Ozone only has 1 lone pair on its central oxygen atom. So that is the difference. Even though they have the same type of shape, their bond angles are different because the number of total groups around the central atom is different, and the number of lone pairs on that central atom is different. That is what attributes to the difference in the bond angles for those two molecules. So for question 33, the angles are different. And the reason why, the central oxygen atoms of those molecules have a different number of total groups, and they have a different number of lone pairs on that central atom as well as a difference in the number of total groups around the central oxygen atom. That is what gives you the different bond angles. Even though the shape is different, even though the shape is the same, the bond angles are different. And the reason for that difference is the different number of total groups around the central atom and the different number of lone pairs of electrons on the central atom. Everyone good with question 33 now? Any other questions? If there are any other questions about models 4, 5, and 6, the last task that you need to do today is go to our eLearn lab page, course content, week 7, and download the Lewis structures for week 9. Download the Lewis structures for week 9 document. Week 9, we're going to focus more on shapes and also polarities. And that's a term we'll discuss in chapter 4. So we won't be doing this lab until 2 weeks from now. But what I'm going to require that you do prior to week 9's lab is that you turn in this completed sheet of drawn Lewis structures for these 17 molecules. So you'll have to draw the Lewis structures for these 17 molecules prior to class. Because before you can successfully complete week 9's lab, you've got to have these Lewis structures already drawn. Now, during week 9's lab, I will give you the key for these Lewis structures. And so for week 9, this is going to be your pre-lab assignment for week 9. You're going to have to get this completed before Thursday, 2 weeks from now. And you're going to have to upload it to a Dropbox. So this pre-lab assignment will count 10 points. So 10 of your total 100 points will come from this pre-lab assignment. I'm not going to grade it based on correctness. I'm going to grade it based on completeness. So as long as you've got a structure, a Lewis structure for me, for all 17 compounds, you will get the 10 points, whether they are totally correct or not. Because I'm going to give you a key for these structures. So you'll know what the correct Lewis structures are you'll be able to confirm that yours were correct or not during week 9 because you'll have access to the key. So therefore, in submitting this prior to lab, it's not going to be graded based on correctness, but just as long as it's complete, you will get the 10 points. So for the rest of the time today, you have time to start working on this so that you can have it finished in 2 weeks. And
What's
so
the due
therefore,
date on that?
Excuse me?
What is the due date on that?
I was just about to say.
Oh, sorry.
Our lab starts at 11 a.m. So you would have to turn it in by 10:50 a.m. on that Thursday, 2 weeks from today. So I'm going to have the drop box to close at 10:50 a.m. So basically 10 minutes before class, you've got to get it submitted. And then once you've submitted it at 11 a.m., I'm going to release the key. So by the time class starts at 11, the key will be released and you'll be able to check to make sure that you got your Lewis structures correct, and you'll be able to use the key or use your own Lewis structures if you got them all correct to help you complete week number 9's lab. So if there aren't any questions about this week's lab, this document is all you need to submit for this week, okay? So submit this completed activity document for Lewis structures to the Lewis structures lab Dropbox by 11:59 p.m. Friday night of this week. That is tomorrow. The week 9 Lewis structures, this is not going to be due until 10:50 a.m. on 10/22. I do think I have that date correct. Today is the 8th, correct? Okay. So we're all adults. I'm gonna let you make an adult decision. You can go back into your group meeting rooms, work on your Lewis structures for week 9. We have an entire hour remaining in our class. Or you can leave class now and work on these at your own time, your own pace. As long as you've got them finished by 10:50 a.m. on this date, you're good. So again, if there aren't any other questions about this week's lab, going once, going twice, make sure you get it completed by 11:59 tomorrow night. Submit only this document for week 7. Save your week 9 Lewis structures and make sure you submit them by 10:50 a.m. on 10/22. And it'll be a totally separate Dropbox I'll set up for submitting these week 9 Lewis structures. The Dropbox will say week 9 Lewis structures. So submit this document to that week 9 Lewis structure Dropbox by 10/22, 10:50 a.m. Okay, everyone good with what they need to submit by tomorrow night and what needs to be submitted 2 weeks from today by 2:50 a.m. Again, if you want to stay in class, go to your individual group meeting rooms to work on these Lewis structures with your team. That is just fine. Or if you want to leave today's meeting, if you're good with our today's lab and you want to go ahead and leave the meeting early, that's fine with me as well. And you'll note on this list, some of these we've already done, haven't we? Some of these we've done already this week. So not all of these will be new. Some of these we've done in class. If you have me for lecture, some of these we've already done. I know we did this one in class on yesterday. So some of these shouldn't be new to you. You should already have the Lewis structures drawn in your notes And for today's lab, for 1, 2, 3, 4, about 4 or 5 of these you should already have. And I know we did this one in my class as well yesterday. And that one too. So if you have me for lecture, you've already got most of these done. Right. So I will let you go back to your group meeting rooms. If you choose to leave the meeting, have a good weekend. Have a good and safe fall break. And for those that I have in my class, I'll see you in class on Wednesday.
Bye. Thank you.
Thank you.
Dr. Cook,
Yes, ma'am.
I was hoping I could speak with you briefly.
Absolutely.
So I was out for the particulate nature of matter lab. I was very sick.
Mhm.
And so that's the only one I do not have turned in.
Okay.
But I also noticed going through my my lab grades, I showed that I
Mhm.
was graded for the very first one,
Mhm.
and then it says dropped right after that.
Well,
And
see, the thing is, you can drop your lowest lab grade. So that's why one of your lab grades are saying dropped, because I haven't graded it yet. So it's still
Okay.
saying 0. And so by that being the first 0, that's why it's saying drop. But once I grade it, it won't say dropped anymore.
Okay.
So these are your 2 options on the particulate nature of matter lab.
Uh-huh.
I do believe that if you go to our teams page where it says posts and
Okay.
scroll up, I do believe the recording for that lab is available.
Okay.
Let's see, particulate nature of matter. Yes, there it is. Chem 1010, section 42, particulate nature of matter lab recording. So you can watch the recording, complete the lab, and submit it, and you will get graded for it. Or you can choose to let that be your dropped lab. I'm gonna let you make that decision.
Okay, gotcha. Yeah, I just wasn't sure because I had seen it was like initially graded. I was like, oh no, what happened? But no, that makes sense. I appreciate you clarifying that.
So yes, just click on that little YouTube link and they'll take you to the recording for that lab. And then you can submit it and I'll grade it.
Okay, perfect. Well, thank you so much for your help.
And in the future, if you need to miss a lab, let me know in advance. And then
Okay.
I'll tell you what your options are.
Okay. Is there a best way of contacting you? I sent a couple emails, but I hadn't heard back, and I didn't have like a phone number for you.
Okay, now I check my eLearn email every day.
So I wonder if you're not getting them because I've sent a couple.
I check eLearn email very often.
Let me see if I can find when I last sent it. Let's see.
You can always email me at my karma.cook@chattanoogastate.edu email as well. I have that email on my phone. So I'll always be able to access email through my chattanoogastate.edu email address. But for class business, I prefer email through eLearn, but it's okay if you email me at my Outlook account as well. The karma.cook@chattanoogastate.edu email address. You can email me at that address as well, and also through eLearn. So,
because the
what's
one
your last name?
It's Valenzuela.
Valenzuela.
Yes, ma'am. Because the one that I sent through eLearn, it's cook@elearn.chattanoogastate.edu.
Uh-huh.
And you didn't
Yeah,
receive.
I should have gotten it. I am so sorry.
Oh no, that's right.
I wonder was eLearn going through some problems because I know a couple of weeks ago there were some issues.
Okay.
Yeah,
because I sent it initially through there. I didn't hear back, and then I was getting a little desperate, and I started writing my notes. And when I was submitting my Dropbox and eLearn, my assignments, I started writing little comments here and there. But
okay.
I just wanted to make sure that there weren't any technical difficulties, or if I was emailing the correct one.
Okay. And I apologize for that.
No, that's fine.
I'm doing a search. Okay. And so that was the week that you were sick, the P&M lab, the particulate nature of matter lab?
Yes.
Okay. All right. I am so sorry I missed that email. But yes, because I missed the email, normally we don't accept late labs after a week past their due date. But because of the mix up with the email, I'll accept it. So did you check in Teams to make sure that you see the recorded video?
Let me go there now.
Yes, so go to Teams.
Okay.
And
you said under files or let me see, or the general room. Let's see, Penny. Oh, yeah. Let's see. Oh, so it says the video's unavailable.